If your hydrogen plant model is built around 1.23 volts, it may look mathematically clean, but it is economically fragile. Because 1.23 volts is not an operating condition, it is a thermodynamic boundary. And confusing boundaries with industrial reality is how hydrogen projects drift from feasibility study to financial disappointment. Let's start with image 1. On the screen you see the equation that connects Gibbs free energy to reversible voltage. This is not marketing math. It is the most fundamental relationship in electrochemistry. The change in Gibbs free energy for splitting water into hydrogen and oxygen determines the minimum electrical potential required to drive the reaction. Under standard conditions, 25 degrees Celsius and 1 bar, that calculation produces approximately 1.23 volts. That number represents perfection. It assumes no activation losses at the electrodes, no resistance through the membrane, no concentration gradients, no inefficiencies. Every joule of electricity becomes chemical energy stored in hydrogen. But this image is showing you a boundary, not a business model. No commercial electrolyzer operates at 1.23 volts because the moment you push meaningful current density through the cell, losses appear. Now move to image 2. Here we introduce the thermoneutral voltage. Instead of Gibbs free energy, this calculation uses enthalpy. And the result, about 1.48 volts, defines a critical thermal crossover. Below this value, the cell absorbs heat from its surroundings to sustain the reaction. Above it, the cell generates heat that must be removed. Modern PM electrolyzers operate around 1.9 to 2.1 volts per cell. That means every real hydrogen plant is operating well above thermoneutral. That red zone shown on the graphic is not theoretical. It represents heat that must be rejected continuously. Cooling loops, heat exchangers, water circulation systems, and auxiliary pumps are all sized around the difference between thermoneutral voltage and actual operating voltage. That difference becomes parasitic load. Parasitic load becomes operating expenditure. Operating expenditure becomes cost per kilogram. Image 3 simplifies the entire voltage landscape into one visual truth. There are 3 voltages that define hydrogen reality. Around 1.23 volts marks the thermodynamic minimum. Around 1.48 volts marks the heat balance threshold. Around 2.0 volts marks industrial operation. The shaded region above 1.48 volts is where cooling systems are mandatory. That shaded region is infrastructure. It is not optional. When someone quotes 1.23 volts without referencing the other 2 voltages, they are describing chemistry, not engineering. Now we move to image 4, and this is where plant architecture begins to shift. This image shows the Nernst relationship. It explains how reversible voltage changes with pressure and temperature. The key insight is not the symbols themselves, it is what they imply. Temperature affects voltage in a relatively linear way. Pressure affects voltage logarithmically. Logarithmic growth means that increasing pressure does raise the reversible voltage, but slowly. Not proportionally, not explosively, gradually. That mathematical behavior is why pressurized hydrogen production is thermodynamically feasible. Image 5 quantifies this effect clearly. At a typical PEM operating temperature of around 80 degrees Celsius, increasing pressure from 1 bar to 30 bar increases the reversible voltage by approximately 0.078 volts. Less than 4% of a 2-volt operating condition. This is the hinge point. The thermodynamic penalty for moving from atmospheric pressure to 30 bar is small. It is measurable, but it is small. And that small penalty opens the door to a major architectural decision. Now examine image 6. Here we compare 2 pathways. On the left, hydrogen is produced at 1 bar and then mechanically compressed to 30 bar. On the right, hydrogen is produced directly at 30 bar inside the stack. Energy consumption is nearly the same. The low-pressure pathway plus compression consumes roughly 56 kilowatt-hours per kilogram. The direct 30-bar pathway consumes roughly 55 kilowatt-hours per kilogram. The difference is marginal, but look beyond energy. The left pathway includes a compressor building. That means rotating equipment, bearings, seals, vibration monitoring, maintenance schedules, spare parts inventories, failure risk, noise, additional footprint. The right pathway removes that entire subsystem. It shifts the pressure burden into the electrochemical stack itself. Instead of managing rotating mechanical stress, you manage membrane pressure stress, energy parity, architectural divergence. Now let's understand where most of the inefficiency truly lives. Image 7 shows the polarization curve. The vertical axis is voltage. The horizontal axis is current density. The reversible voltage sits at the bottom. Above it, activation losses appear first, the energy required to initiate electrochemical reactions at the electrodes. Then ohmic losses dominate, resistance through membranes, contacts, and interconnects. At higher current densities, mass transport limitations begin to contribute. The total gap between reversible voltage and industrial operation is often 700 to 800 millivolts. That gap dwarfs the 0.078 volt penalty introduced by raising pressure from 1 bar to 30 bar. This is critical perspective. Pressure correction is minor compared to intrinsic electrochemical losses. Material science and current density optimization matter far more than moderate pressure increases. But survivability is not just about efficiency, it is about resilience under stress. Image 8 shows the structural fork in the road. On the left, we see the low-pressure electrolyzer feeding a compressor building before storage. On the right, we see a pressurized stack feeding storage directly. The left configuration introduces mechanical complexity. The right configuration introduces higher electrochemical pressure stress, but eliminates rotating machinery. Under ideal laboratory conditions, both systems can operate. Under industrial conditions, complexity compounds. Now look at image 9. This is the competitive edge test applied to hydrogen architecture. Imagine electricity prices spike. Imagine utilization drops below projections. Imagine policy support weakens. Which configuration survives longer? The one with more rotating parts, more maintenance exposure, more mechanical downtime risk? Or the one with fewer mechanical subsystems and simpler flow paths? Pressurized stack systems often demonstrate stronger resilience because they reduce mechanical exposure. Electrochemical degradation is gradual and measurable. Mechanical failure can be abrupt and operationally disruptive. This is the sustained systems cleantech framework in action. Sustainability is not just about carbon intensity, it is about economic survivability under stress. Systems that simplify architecture while respecting thermodynamic constraints tend to survive longer in volatile markets. So why do hydrogen plants run at 30 bar? Not because it dramatically reduces energy consumption. The Nernst correction is small. Not because it makes electrolysis magically efficient. Overpotentials still dominate losses. They run at 30 bar because the small thermodynamic penalty is outweighed by the architectural simplification. Removing compressors reduces capital complexity, maintenance burden, rotating risk, and subsystem fragility. It concentrates complexity inside electrochemistry, where scaling is modular and predictable. The decision is not emotional, it is mathematical and systemic. There are 3 voltages that anchor hydrogen reality. Around 1.23 volts defines the thermodynamic floor. Around 1.48 volts defines the heat crossover threshold. Around 2.0 volts defines industrial operation. The Nernst relationship shifts the floor slightly when pressure increases. Overpotentials dominate real-world losses. Architecture determines survivability. If your voltage assumptions are wrong, your cooling load assumptions are wrong. If cooling assumptions are wrong, auxiliary consumption is wrong. If auxiliary consumption is wrong, your cost per kilogram is wrong. And if cost per kilogram is wrong, your financing structure fails under scrutiny. Hydrogen does not respond to optimism. It responds to physics, kinetics, and system design. 30 bar is not a marketing number. It is an engineering compromise that respects thermodynamics, acknowledges real-world losses, and simplifies plant architecture in a way that improves survivability under system stress. Physics sets the boundary. Engineering defines the gap. Architecture determines resilience. And physics always wins.